Welcome back to the Udimking Education Foundation Masterclass series. Today, we are walking through a comprehensive step-by-step resolution of Example 2, focusing on the mechanics of constant volume gas thermometry. On the screen is our Example 2 question. Let's begin by reviewing our problem profile. A constant volume gas thermometer registers a pressure reading of 250 millimeters of mercury at the ice point and scales up to 750 millimeters of mercury at the steam point. Our core task is to determine the absolute thermodynamic temperature value on the Kelvin scale when this specific instrument registers an intermediate reading of 450 millimeters of mercury. Looking at our options ledger, we have 40 Kelvin, 233 Kelvin, and 333 Kelvin. To solve this systematically, step 1 requires us to map our system reference boundaries using our universal linear blueprint. This formula states that the ratio of change on our property scale must equal the ratio of change on our temperature scale. Visually, we align two vertical tracking tubes side by side. On our left pressure axis, our lower fixed point, represented by the variable small a, is anchored at 250 millimeters. The upper fixed point, small b, is anchored at 750 millimeters. Our active intermediate reading, large X, sits at 450 millimeters. On our right Kelvin reference axis, our lower fixed point, small c, is mapped to 273 Kelvin. The upper fixed point, small d, is mapped to 373 Kelvin. Our target temperature variable, large Y, represents our unknown absolute value T. Step 2 is core parameter substitution. We inject our isolated property markers directly into our blueprint fraction blocks. This transforms our balanced equation into 450 minus 250 divided by 750 minus 250. This left side is set equal to the Kelvin side expression, which reads T minus 273 divided by 373 minus 273. In step 3, we evaluate our fundamental range intervals by calculating the direct mathematical differences. On the left side, our active pressure climb is 450 minus 250, which gives us 200 millimeters. The total baseline span is 750 minus 250, which gives us a fundamental interval of 500 millimeters. On the right side, the baseline Kelvin interval simplifies perfectly to 100 units. Our expression now simplifies cleanly to 200 divided by 500 equals T minus 273 over 100. Reducing the left-hand fraction yields a precise climbing ratio of 0.4. Step 4 brings us to algebraic balancing. Multiplying 0.4 by 100 yields exactly 40 units. This leaves us with a beautifully simple linear balance equation. 40 equals T minus 273. Finally, in step 5, to completely isolate T, we pass our freezing offset of 273 to the other side of the balance as an addition. Our final calculation becomes T equals 273 plus 40, which resolves with total mathematical certainty to exactly 313 Kelvin. Checking back against our examination sheet, this result perfectly matches option C. By applying linear interpolation scales, you have verified this solution from basic principles. Thank you for learning with the Udimking Education Foundation. Keep up the excellent work, and we will see you in the next module.
Udimking Education Foundation. Building confidence, ending examination malpractice for a better tomorrow.
We are building a better tomorrow.
Join us in shaping futures through integrity and education.